So welcome to those of you on Zoom and in person. As I mentioned this morning, the morning speakers were from EMBER, this consortium studying the fire and focused on the estuary itself. Your afternoon speakers are from a variety of institutions and are looking above the tide line primarily at the larger watershed and terrestrial impacts and human impacts. So our first speaker in this afternoon session is Peter Weiss from UC Santa Cruz.
Okay, thank you. Thanks, everyone. Appreciate being here. I'm going to tip this up a little bit because my head's being cut off. I'm maybe a bit taller than the other speakers.
It's on the owl.
Okay. Well, anyway, there we go. That probably works. Okay, so I'm going to talk about the atmosphere, and this is the most easily contaminated medium that we have on this earth, right? I mean, like a puff of smoke comes up and instantly everybody's affected. Now, the good news is it goes away after a while, right? The atmosphere is not currently being impacted by the battery fire, whereas like the estuaries and sediments still have that record. But talk about tragedy of the commons, the atmosphere affects all of us. Like there's no way. We all live downstream, and the pollution affects so much. So I also want to mention that unlike a lot of the other things that have been presented so far that had funding and people have been working on this for many, many months, my study was done very quickly with absolutely no funding. So I basically, thank you. So this is more like citizen science, okay? This is not part of my regular job, even though I'm with the Department of Microbiology and Environmental Toxicology at UC Santa Cruz. So anyway, because I knew how to run the tool that I'm going to present to you, I was able to look at answer some questions, at least examine them. And the tool is called HiSplit, and it is a weather model that you can run in reverse and forward. So if you have a point that is emitting pollution, you can determine where it was likely that the pollution went to. Or if you are at a receptor location, you can see where likely the air came when it arrived to you. Okay, so you can run it in these two different modes, and you'll see examples of both of those. So I wanted to find out, can we determine where the battery fire plume traveled in the days after the fire began? I also want to acknowledge MBARD, Monterey Bay Air Resources District, for providing me with the data on the particulate matter, the PM 2.5 from their Clarity sensor network. So it's like 20-something different sites around the region that are collecting data every 5 minutes or something. So I was able to look at that, sort of the regional picture of the particulate matter in the atmosphere, and see how that compared with what the HiSplit model was telling us. And then we also had some local wind speed and direction data from a few sites around the region. So let's just get a picture of this, see, does it make sense? Can we use the HiSplit data to sort of understand it better? Because obviously we have a lot more capabilities with the model than we do with the measurements. So let's talk about HiSplit. This is available to the public. In fact, if anybody really wants, a demo on this sometime, just contact me. I'll be happy to go on Zoom and show you how to use this model. It's pretty easy. It's fortunately, it's still up on a federal government website. So for now, we're in good shape. You can choose different models to the HiSplit will run with different weather models. So I choose the HRRR, which is the highest resolution model that they offer, and it has 3 kilometers spatial resolution. So that's not bad, right? 3 kilometers is a pretty big square in this area, but the largest ones are like 25 or 100 kilometers. So that would be way too big for what we're talking about. I set the starting location of the battery facility. You can change all these parameters, and you get a different result depending if you tune it differently. So you got to take your results with a little bit of grain of salt, do sensitivity testing. But reasonable assumptions, set the top of the plume at 200 meters, and it basically releases a bunch of particles, which they're inert, they don't do anything, they just stay in the air, and they're released just like a puff for 10 minutes, and they travel for 1 hour. So assuming that the battery fire was just a temporary puff, and we can see where it went to. So I'm just going to show you a bunch of maps here. This was the output of the model, so you can kind of see. And this down right here is the time. So January 16th, this is in the morning. So this is before the fire. And you have to remember it's winter time. So the normal land sea breeze that we have for most of the year is not really happening. It's more either like no winds or the winds are kind of from weird directions. The transport pattern is not normal at this time of year. And there can be very low temperature inversions too, because there's not a lot of sunlight at this time of year and the ground gets very cold. So you have very shallow nocturnal inversions. But this is before the fire. The air is going offshore. This is right before the fire. There's not much wind at all. You can see the transport's kind of going in every which direction and doesn't go very far. And then right at the beginning of the fire, you can see the winds have shifted throughout the day and due east. Okay, so I think this matches with what a lot of people see with the deposition at Elkhorn Slough. At this time, you can see in the next hour, it's already starting to rotate. The winds are now pushing, they're coming from more of a southerly direction. They're pushing it more to the north. It's still impacting Elkhorn Slough pretty severely. And it's twisting around, going more, and it's hitting Watsonville. This is in the evening, more in the evening. And now it's actually starting to go offshore a bit more. It's heading up towards Santa Cruz. This is only 1 hour of transport. Okay, from the fire. So you can imagine after 5 hours, it's gotten all the way to Santa Cruz. And I know that, you know, people who live in Santa Cruz, we could smell stuff in the air. So we know it came up there. And those were the hours when it went up there. Okay. And as the days is shifting on, now we're into night. And you can see northerly, it got a pretty good hit. Okay, for like a good 6 hours. Now it's kind of less winds. And so this is a lot of the overnight period. So that first day was definitely east, north, a little bit offshore, and not going very far. So kind of just staying in that Elkhorn Slough area. This is aggregated over the first 12 hours after the battery fire. So you can see this just sort of adds it all together. This 12-hour average. So you see got Santa Cruz, mostly north. For the second 12 hours, things shifted around. Now you can see it's starting to go to the east. So as I'll show in the particulate data, Hollister had a peak in the particulate matter data, 12 to 24 hours after the start of the fire. And that's because the wind shifted around and finally went out to Hollister. The third 12-hour, so this is like 36 hours after the start of the battery fire, we're in great shape. All the pollution's going out to sea. Okay, so that's really good for people living on land. Maybe Pacific Grove got a little bit then. But then in the fourth, and so now 48 hours later, I find this amazing. Look, all the pollution went down to Salinas Valley. And this is when you see the peak in the particulate matter in places like Gonzales, Soledad, and so forth. Okay, I'll show you that. So that's what the high split model shows us. Now the clarity data from MBARD, these are all their sites. So you can see it's pretty good coverage. There's nothing really right next to the battery fire. Watsonville and Salinas are kind of the closest ones, but it does give you a regional picture. This is the closest one at Aromas School to the battery fire. And the concentration peaks up at just before midnight on the January 17th. So that was the closest site to the fire and also the nearest Plume arrival time. The picture on the right, which I'm not going to really explain very much, but I'll just say this is the high split model in the backwards direction. So the receptor location is the Aroma School, and that is the model telling us where the air came from to arrive at Aroma School. And then this stuff down here is the altitude of the transport. So you can see it's all very low altitude, which means that it would have picked up pollution from surface sources. Okay, and I'm just going to buzz through these. You can get your favorite location. Similarly, Watsonville, you can see the peak. The red line is the battery fire, and the peak and the concentration of the particulate matter doesn't happen for like 10 hours later. Okay, so this is why it took a while for it to get over there, and I can discuss why I think that is. San Juan Bautista, similarly, it sort of happened later. Hollister, still, it's a good 12 hours later. Here's Gonzales. I don't have the red line, but you can see the peak is happening it's like on the 18th. So it was a good bit of time before the particulate matter concentrations went up. Okay. Local wind measurements. I just have one slide on this. There's a lot on here, but you can see there's winds measured at Elkhorn Slough, and those little pie slices show you where the winds are coming from. So there was definitely winds from the west that would have gotten stuff from the battery fire. At Watsonville, you can see this slice over here from the southwest. That definitely would have brought pollutants. Similarly, this slice of Pajaro, winds were coming from the southwest, and that would probably pick up pollutants. And then at De La Viega up in Santa Cruz, not much. Okay, it's just really, they didn't really get any winds from this southeast direction that would have picked up pollutants. And you can see that these numbers are the particulate matter concentration. So up in De La Viega, it was pretty low, whereas down in San Juan Bautista, it was quite a bit higher. Okay, so real quick, I'm happy to take questions on this, but I can expand more on some of these points. So the battery fire plume was diluted and dispersed over a large area thanks to variable winds and transport. Okay, so every 12-hour period, the wind was blowing in a different direction. So it really marched around. No region was spared, which is bad news, but no region got huge hits. Okay, maybe the nearer to Elkhorn Slough is probably the worst. The plume arrivals were more than 24 hours after the beginning of the fire at locations of the Salinas Valley and elsewhere. And because there was quite a bit of dilution, and I think the initial plume was so hot, it went up above that boundary layer, which was kind of shallow in that January time period. Once it got above the boundary layer, those pollutants were headed out to the Central Valley and areas beyond. And so as a result of that, the particulate matter concentrations at all sites were less than 35 micrograms per cubic meter, that's the 24-hour health threshold. And so from a particulate matter standpoint, there was no measurements that exceeded the health standard for air pollution, which is ironic because it was such a large, fire and disaster. And there was certainly a lot of particulate matter that came out. But as far as where it was measured, there was no air quality exceedances. And just comparing the model with the wind direction and the particulate matter data, they seem to all, agree pretty well. So that's hopeful that we have the tools that we can paint a picture, we can understand, after the fact, what happened. And hopefully we can get more monitoring in place, going forward. These particulate sensors are really inexpensive, and they should be, a lot more locations so we can catch those local effects. So that's it for my thought. Yeah.
I live by the Monterey Bay Aquarium, so right near PG, and starting the night after the fire started at 11 p.m. I called my mom and I said, I can taste metal on my tongue. I think this is related to the fire. It feels very weird. And so it's nice to see that reflected in the data as well. Yeah.
Yeah, it makes sense.
So Peter Brango would never get lost lighting.
Yeah.
It's nice to meet you.
Yeah, nice to finally meet you. For sure.
Early on.
Yeah.
And your data is so important.
Thanks.
But here's the key question I need to ask. What we've learned is that in a thermal runaway events, the material is broken down to less than 1 part per billion. And my question for you is, do you know, in the high splits, if you're measuring below the 2.5, and if I may, a quick preface, my understanding of 2.5 was detected at higher levels in places like Carmel Valley and the San Lorenzo Valley because people are burning their wood-fired stoves in the winter. So the Air Resources Board has pointed to the fact that they saw higher numbers elsewhere than what they were finding monitoring the fire. This is on the record. Therefore, my question is, were they measuring for what we now know was actually coming out of that fire, which was smaller in many, if not most instances, than 2.5 microns?
So like you're saying 1 micron, not 1 ppb.
Thank you. Yes.
Yeah, 1 micron.
1 micron. Or smaller.
It's hard to say because there are so many mixtures of sources. You've got wood burning because it's January, and you've got these inversion layers that can persist all day, especially in places like San Lorenzo Valley. So that just the wood smoke can build up.
But the question is, was the monitoring for less than 2.5? We know that 2.5 and above is being detected all over the place.
Well, the
What- what is the
2.5
number below?
is 2.5 and below.
Yes.
Yeah.
Oh, so it was below.
Yes.
Definitely being measured out. John, look, as much.
Yeah, because the larger particles, they don't make it into the sensor. Because they're just too big. So if there's like a twist in the air path, that particle will just hit the side and it won't go in. But anything smaller than 2.5 does go in. So it represents the total
A
particle.
quick follow-up,
Yeah.
is there a way to differentiate between the volume of 2.5 and the volume of point, for example, the volume of 1 parts per billion coming through?
There is, but with these cheap sensors, no.
All right.
There's only 3 like EPA approved particulate instruments in this area, Salinas, Santa Cruz, and somewhere else. But yeah, and they're measuring at all the different size ranges.
Thank you.
But that's only 3 locations in this
Right.
whole huge area.
So the majority of the testing
Yeah.
sites were not measuring below 2.5.
Right. Yeah.
So that's actually an important detail, because there weren't any sites set up near the fire that were measuring for the actual potential size of the particulate matter coming out of that fire.
And certainly we're measuring larger particles as well.
Understood. Thank you.
The particulate matter concentrations at all sites were less than 35. That statement has come across and proven by Mr. Stedman as there's no pollution. Okay, now, so if smaller items were actually in there and were causing people, like the 1,300 people that reported symptoms, and like me, that choked out on the 18th of January because I swallowed something. We know from our communities that there was a problem.
Yeah. Well, yeah, no, I mean, I think the date, I mean, that statement is factual based on the
And
measurements.
it's
So,
here as-
but how it's interpreted is a different story. And I think what is missing from that number is the PM10, the larger particles. And those are the kinds of particles that are going to get lodged in your throat.
That's a piece of information that would help the community. Thank you.
Yeah.
Michael?
And what's really important relative to that number, 2.5,
Mhm.
is the composition, what is included in that number.
For sure.
Okay, now, in Carmel Valley, as your example, you know, that there were some exceedances, but that was other things. That was, you know, agricultural dust. That was wood burning fireplaces and so forth. But what was in our plume, that number is significant because that was cathode materials. That was nickel, manganese, cobalt, lithium, right? That's been proven by our sampling. So what's important here is, well, you know, yes, the submicron sizes are captured in the 2.5. But it's the composition of that plume which is important. And that answers your question there. You weren't breathing just regular agricultural dust. You were breathing a chemical fire, the same dust.
Yeah, no, I agree.
If they measured less smaller things, it's not reported what smaller things were. All we get told is 2.5, it's blanket. I'm not gonna tell you what's in it.
Yeah, well, we don't have the ability to do that.
Yeah.
You know, that's the problem. And even these numbers are, you know, with the little handheld thing, and we don't even know how its accuracy. They were never designed to provide regulatory or even this, you know, high level scientific information that we're wanting from the data. These measurements are just kind of like, oh, it's sort of high over here and sort of low over here, you know, for like forest fires or something like that, where you kind of, you know, it's different than an industrial accident.
Don?
Maybe that's great. So I have a question kind of related to this. So we know from what you just showed that the density of the sensors is relatively low. There are very few of them. And my question is, for the high split model, it's using the actual measured values from each sensor and
No.
percolating.
No. Yeah, I sorry, I didn't explain that properly. So it doesn't use any actual measurements and it doesn't use any particulate data at all. All it's doing is it's like a gridded weather model. So it can tell you, you know, if you're here, the winds are going to push you in this direction at this speed. And for the actual dispersion modeling, it releases like a puff of just made up particles. And then each one of those particles goes in a different direction based on the winds, as it would normally. So it's trying to simulate, if you set up a puff of, baby powder, where would all those pieces go? So it's modeling that.
Okay,
Yeah.
so for the statement about the number of concentrations exceeded 35 micrograms per cubic meter, that's based on the actual.
The actual measurements, yeah, from those
Knowing
sensors.
that the density of the sensors is relatively low.
Yeah.
no Coverage.
Yeah.
It's quite possible that in areas that were not covered by the sensors, the levels could have been much higher.
Oh, yeah,
And so
certainly.
is it possible to sort of put some confidence limits on a value like that to get a sense of, when you get a negative answer like this?
Yeah.
Is it really negative, or is it just I couldn't tell because I didn't have the density of sensors to measure it?
The density of sensors is definitely a problem because, if we go back to the picture of where they are, this one right here, I mean, you can see for yourself, I guess that Aromas one is just to the right of the word Watsonville. So that's the closest one. It could, where the Plume was going, and then Watsonville was the next closest one. But, those are like 10 miles or more. So yeah, you're missing a whole area there that is, well, obviously experience a lot of fallout. So the large particles, I think, were significant. As you get all that volatilization of the materials, once it cools off, they naturally condense into large particles. And then anything larger than 10 microns is going to fall out within a couple hours. So those particles never made it to the sensors. So that it's an incomplete picture. I think what, in defense of Richard and Mbard, they're not used to looking at events like this, right? So they're used to looking at like forest fires or, things where it's like huge levels of, vast dispersal of smoke. This was like coming from one tiny little point. And so if you're like over here, it's different than if, the variation on a small scale can be really, really large.
We just have time for one more question from Zoom. Could you step onto the stage so next you come here and the next?
Yeah, for sure.
Thank you. This is from the Zoom, and I'm going to merge these two because they're related. So maybe you two here, Peter. I was wondering what the particle size distribution was that was used in the Plume modeling to determine deposition of larger particles near the source and longer range transport of nanoparticles, ? And then as part of that also, what source term did you use and how did you develop it?
Yeah, unfortunately, none of that applies to what I just talked about. So the high split model, like I said, these are imaginary particles, and it's just telling you, like, if you sent some particles up, where are the winds going to take them? So there was no like actual based on the measurements or anything like that. Yeah, if you have more questions about how exactly that works, please email me and I can try to clear that up.
And we will have an interactive session as our last hour today where you can ask questions of any speakers too. But thank you, Peter.
Yeah, all right.